Sora has taken the internet by storm since its initial revealing by OpenAI back in February this year. Today, I'm very excited to start this new series called The Anatomy of Sora, in which we're going to discuss the evolution of vision model from its very basic form to the powerful foundational model such as Sora we see today. We're also going to cover the internal mechanisms of Sora, such as its encoder, decoder, as well as how it's potentially trained. Even though the public version of Sora has not been released, just from some of the demo released by OpenAI, we can already see the power of this video generative model. As we can see in this video generated by Sora, two mammoths are running towards you. You can feel the energy of this prehistorical creature running at you. The snow stirring up behind their feet make it even more realistic. This second clip, also generated by Sora, is more of a video game style cinematic video. It looks very stunning and futuristic at first, but if you look a bit closer, some of the background objects are a bit rough and the movement is quite stiff. Perhaps the initial version of Sora is having some limitation in generating multiple different objects and their movements. For example, you can see the person in red hoodie is having very stiff movement. This, I believe, will gradually improve as the later iteration of model starting to come up. Here are some of the top industries that I think are most likely be disrupted by Sora. The first one is video advertising. As we know, advertising is a $1 trillion business. Just last year, YouTube's global advertising revenue is around 31.5 billion. Similarly, Instagram generated ads revenue closer to 30 billion last year as well. So it's a huge industry. And this is because video ads is a super effective ads format in that it can capture audience attention, deliver rich information about the product or the service, and spread brand awareness. However, the high cost of video ads production is setting a very high bar of entrance for many smaller advertisers with tight budgets. I believe large vision generative models such as Sora is going to drastically lower the cost of video ads production and transform the ads industry to embrace this more effective ads format. The next industry I think will be disrupted is education, and more specifically education tech. The US education technology market alone had around 70 billion in revenue in 2022 and is growing at the rate of 16% compounding annual growth rate in the last 5 years. This is a very stunning growth rate. The K-12 and the pre-K segment accounted for 41% of the market value. The edtech market is expected to grow to 388 billion by 2030, so it's definitely a huge market to capture. Many education content are still very primitive and is based on text, image, and diagrams. Imagine in the near future which we can have video generated for specific topic such as science and physics and chemistry, and even personalized video generation tailored towards each student's learning style. The other industry that will be supercharged by Sora is film industry. The average cost of CGI video production for US film is around $33 million per movie. For the Academy-winning movie Avatar: The Way of Water, the vision effect is costing them $250 million because it has over 4,000 visual effect shots. Just to be clear, I don't think AI or Sora is going to replace human labor because filmmaking is more of an art. But what I believe is it will definitely accelerate the filmmaking process and bring down the cost, thus enable and empower more indie filmmakers to unleash their imagination and creativity. The other industry that will think be largely affected and largely empowered is content creation industry. The global digital video content market was valued at 139 billion in 2023 and is continued to grow at a rapid pace, especially for platforms such as TikTok, which has generated 16 billion in revenue last year, is increasing at a stunning rate of 67%. Content creators on both long-form content platform and short-term platform will benefit from this large video generative model such as Sora. That being said, these are the four industries that I think will be transformed by Sora and unlock many potential use cases. Next, my friend is going to cover the evolution of vision models that led us to Sora. So let's hand it to him.
There are a few approaches to solve the video generation problem. We will describe each individually and afterwards compare them. In addition, we first simplify to image generation problem before extending it to video generation in episode 2. Also, on all approaches, we discuss the unconditioned version prior to the conditioned generation. The first one is variational autoencoder or VAE. It is a bottleneck or hourglass network where some form of feature compression and expansion occurring within. The network is trained to reconstruct input images. Let's first describe the components of the diagram. This diagram is the training version of VAE. On the left and right, we have the input and reconstructed images. We reformat them to vectors for visualization purposes. This way, they can be removed from the diagram. Next, the arrows are used to denote input into the next module. Last is the network itself. It is comprised of an encoder, middle bottleneck latent space representation, and a decoder. Note that the encoder trapezoid depicts feature downsampling or compression subnetwork. The abstraction can represent a set of neuron layers with decreasing number of nodes, decreasing size stacks of CNN feature maps, or decreasing size spatiotemporal feature maps. Correspondingly, the decoder trapezoid is an upsampling or expansion network. Diving into the latent space, the variational representation is a multidimensional Gaussian distribution denoted by means and standard deviation. This is why we illustrate the representation by putting a disk in a rectangle in previous slides. The distribution tries to absorb and be robust against empirical invariances introduced by the dataset and training. Training augmentation can be done by adding noise via corrupted training images and/or noise in latent space. VAE networks are trained using pixel-wise reconstruction and regularization error. The reconstruction loss accounts for pixel value differences, which can be done using, for example, mean squared error. The regularization loss is a KL divergence to encourage the latent space distribution to be Gaussian. During inference, we discard the encoder part and run just the decoder. By inputting a random latent feature, we can construct a random image. This is the unconditioned image generation. For conditioned version of VAE, we inject a condition onto the network to output a specific image. It can be a class, for example, a bison, or an encoded text, for example, a bison drawn in cartoon style. It can also be both text and image condition, for example, for image translation. Other image condition can be an edge map, a depth map, or an altered original image, such as for editing. To do this, we also use the encoder for inference. An important addition to image condition VAE is skip connections. Skip connections relay activation map from a set of encoder layers onto mirror decoder layers. They are added to alleviate vanishing gradient during compression, as well as to add information and supervision during upsampling. A well-known name for such network is the U-net. The network received its name because of the encoder-decoder U-shape when arranged flat horizontally on the bottom. VAE models, however, have a general issue for generating blurry or low fidelity images. This is because the algorithm also wants to produce a robust representation and enforces a Gaussian latent space. In addition, it often uses what is effectively an L2 smoothing loss. The second approach is called Generative Adversarial Network or GAN. It produces high resolution images because it focuses more on outputting samples and not saddled with having to simultaneously create representation. It does so by having two separate modules, generator and discriminator, as shown in the figure. The generator first tries to create high quality images. The discriminator is then shown a random image that can come from either the dataset or the generator. Its task is to predict which one is which. Like VAE, the generator can be unconditioned, producing an image from random seed. Or it can be conditioned, for example, by incorporating an encoder to accommodate image-based conditioning. The approach uses min-max GAN loss, where generator tries to minimize the loss by fooling the discriminator. The discriminator, on the other hand, maximizes the loss by producing correct prediction. In a sense, the discriminator learns an image quality function. The conditional version of GAN is often trained with reconstruction loss on the generator. However, this can clash with the adversarial objective. Training in such an adversarial framework is difficult. The alternating freezing and updating of weights between generator and discriminator can produce oscillation with no convergence. Another issue encountered is mode collapse or lack of diversity in producing only few distinct samples to achieve equilibrium. This often occurs once generator stops learning when it falls behind the discriminator. One possible reason is that there may be more sophistication or randomness required during the generation process. This is addressed by the next approach, the diffusion models. The diffusion models, the third approach, is currently the most popular and commercially available among the three. Diffusion models learn to take inspiration from both VAE and GAN. It incorporates VAE representation power while being mindful of its blurry outputs. In addition, it further develops GAN sample creation by increasing variety, uses of multiple steps, and not rely on adversarial training. Just like VAE and GAN, the model consists of an encoder and decoder at both ends. However, these stages perform a milder compression in that it only removes the most unnecessary signals. Therefore, the latent map is only slightly smaller than the original image for the diffusion process. The diffusion process itself is far more computationally complex than the other approaches. This iterative process is performed many times, up to 100 iterations, through comparable networks as GAN or VAE for more stable refinement. Furthermore, the many steps at larger latent space allows for introduction for more noise for diversity and conditioning injection for faithfulness to the instruction. The diagram illustrates both the diffusion at the top and reverse diffusion or denoising process at the bottom. Only the denoising process is performed during inference. Sora is a diffusion model. It is likely the biggest generative model in existence. The displayed Sora diagram is deduced using the technical report. The encoder and decoder are now extended to video generation. The model generates coherent stack of images as a single video. The encoding process utilizes native resolution vision transformer or NAVIT and spatiotemporal vision transformer or VIVIT. The first technique, NAVIT, means Sora does not resize the input image to a canonical size, instead keeping the original aspect ratio. The second one, Vivid, is the use of spatiotemporal filters or stacks of image regions across space and time as one volumetric unit token. The diffusion process itself uses a transformer architecture rather than a unit. This allows for latent map to maintain the same size throughout the layers. We focus more on the encoding stage in episode 2, which also includes the transformer and vision transformer discussions. Episode 3 is dedicated to the diffusion process. It takes us through the original diffusion architecture all the way to the fusion transformers. Finally, in episode 4, we discuss the training process, which includes the multiple tasks used to train Sora. The episode also discusses in details what Sora accomplished. To end, we show the high level differences between the approaches. Thank you.